Hello there, Mr. Sutton here, bringing you the AB Calculus 513 Extra Practice number 4 solutions on average value. To find the average value of this function over the interval from 0 to 1, we're going to start by taking 1 over the interval length, so 1 over 1 minus 0, times the integral from 0 to 1 of the function we're trying to average, which I'm going to rewrite as x to the 1/2 power, and then a dx there. So let's see here. This is just 1 on the outside, so I don't really have to worry about it. Antiderivative of this, we're going to bump this up to a 3/2, and then dividing by 3/2, we're really multiplying by 2/3. So we've got 2/3 x to the 3/2 evaluated from 0 to 1. I'm going to yank out this 2/3, and inside my parentheses, I'm going to have, let's see here, this is the square root cubed of 1 minus, same deal, with 0. So this is really just 1 minus 0, which all comes out to just 1 inside there. So when all is said and done, we get 2/3 for our average value. For this problem, we want the average value of secant of x tan of x over the interval from negative to positive pi over 4. So to get this, we're going to do 1 over the interval length, which is 1 over pi over 4 minus negative pi over 4, or plus pi over 4. We're going to do that times the integral from negative pi over 4 to positive pi over 4 of f of x, so secant of x tan of x dx. Cleaning this up a little bit, this down here is really going to be 2 pi over 4, which is really pi over 2 down there. And let's see, we need the antiderivative of secant of x tan of x, which conveniently is just going to be secant of x, and we're evaluating that from negative to positive pi over 4. So let's see here. This is really 2 over pi if I same change flip this thing out here. And I'm going to be multiplying that now by parentheses. So inside we've got secant of pi over 4 minus secant of negative pi over 4. So let's see. Secant of pi over 4, that's really going to be 1 over cosine of pi over 4. Cosine of pi over 4 is root 2 over 2. So reciprocal of that's going to be 2 over radical 2. And then this is going to be 1 over cosine of negative pi over 4. So negative pi over 4, that's actually the same thing as positive pi over 4 when you take the cosine. So this is another 2 over radical 2 then when we take the secant of this term. So we're doing 2 radical 2 minus 2 radical 2. All this stuff in here comes out to 0. That zeroes out the 2 over pi over there. So we get a grand total of 0. To find the average value of this function, let's start by doing 1 over the interval length. So that's 1 over 1 minus negative 3 times the integral from negative 3 to 1 of 2x dx. So this is going to be 1 over 4. And this antiderivative, this bumps up to an exponent of 2. Dividing by that, we just have x squared, evaluated from negative 3 to 1. So we have 1/4, and in a parentheses, we're going to have 1 squared minus negative 3 squared. So this is going to be 1 minus 9, which comes out to negative 8. 1/4 of that gives us negative 2. To find the average value of 3e to the x over this interval, we're going to start with 1 over the interval length, so 1 over 0 minus negative 1. And that's going to get multiplied by the integral from negative 1 to 0 of the function here, 3e to the x, and then a dx. So this out here, this is really just 1 over 1, which we can pretty much forget about. Antiderivative of 3e to the x is also 3e to the x, and we're evaluating that from negative 1 to 0. So this is going to be 3e to the 0 minus 3e to the negative 1. If you really wanted to, I mean, you don't have to simplify this because it's all constants at this point, but this is really just going to be 3 minus 3 over e, which you could just keep going, but I'm just going to stop there. To find the average value of this function with a calculator, let me just first set up what I'm about to do on the calculator. So I need to do 1 over the interval length. That's 1 over 1 minus negative 3. Multiply that by the integral from negative 3 to 1 of whatever I'm trying to average, which is this whole function here. I'm just going to call that f of x since they already named it for me. No point in rewriting it. Let me do this on the calculator now. To get the ball rolling on this one, I'm going to enter my function here as y1, just to make it a little easier to plug in. And then if I quit to the main screen here, let me write all of this out now. All right, there we go. We've got our fraction out in front, our integral, which I did Math 9 to get. I did alpha trace to pull up the y menu with y1 in it, dx. And then if we press enter, all that comes out to 1/3, 0.333. On this one, we have the graph of a continuous function f, and we want the average value of f over the interval from -1 to 6. So I'm going to set this up using my average value format with integrals. We'll start with 1 over the interval length, so 1 over 6 minus -1. And then, let's see, I'm multiplying that by the integral from -1 to 6 of the function I'm trying to average, in this case f of x, and then we have a dx in there as well. So this is going to be 1 over 7 times, and now to actually calculate this integral from -1 to 6, I just have to take some areas. So let's see here, I've got a trapezoid from -1 to 4 that I can use. So this is going to be a base of, let's see, base of 5 plus a base of 4 over 2 times a height of 2. There we go. And then over here we have another trapezoid. This time I have a base of 2, a base of 4, so 2 plus 4 over 2, and a height of 2. So simplifying this a little bit, these 2's are going to cancel. I've got 1/7 and I have a 9 in parentheses. Plus, well, hey, these 2's cancel also, so that's a 6. So this is 1 over 7 times 15, or 15 over 7, which is going to give us choice C. For this one, if the average value of some function f on the interval 1 to 4 is 8, what's the value of this other integral on the interval from 1 to 4? All right, so the way I'm going to do this one, they're giving me a little bit of information about this average value. So I'm going to set up an equation involving the average value, and that's going to give me a little bit more clarity on something that I can use to figure out this other integral. So, average value. We have 1 over the interval length, so that's going to be 1 over 4 minus 1. So I'm basically going to pretend I'm taking the average value here. And I have an integral from 1 to 4 of f of x dx. So this is just the average value of my function on this interval. Now they said that this has a value of 8, so I can write literally here equals 8. Well, if this is the case, this is really 1 over 3 over here. I can multiply both sides by 3 to get that the integral from 1 to 4 of f of x dx just by itself equals 24. Now where this is going to help me out is in figuring out what this other integral comes out to. So this other integral, I'm actually going to split this up a bit. So there's the integral they gave me. I'm going to split this up into integral from 1 to 4 of 3f of x plus integral of 1 to 4 of 2x. And for this first piece, I'm going to pull that 3 outside the integral as a multiplier. And then I have plus integral from 1 to 4 of 2x dx. So going a little further on this one, I have 3 times this integral that I just figured out up here has a value of 24. This is really 3 times 24. Over here, integral of 2x, I need to take the antiderivative and use my fundamental theorem. So this is going to be x squared evaluated from 1 to 4. Going further still now, because I have to actually get a number out of all this, 3 times 24, that's going to be 72. And then evaluating x squared from 1 to 4, that's really 4 squared minus 1 squared. So when all is said and done, we have 72 plus 16, which is 88, minus 1 is going to be 87. So that's going to be choice D. On this problem, I'm just trying to find the average value of this f of x function on the interval from 2 to 6, and they let me use the calculator, so I'm just going to write my setup, and then I'm going straight to the calculator. So for average value, I need 1 over the interval length, so that's 1 over 6 minus 2, times the integral with these limits in here, so integral from 2 to 6, of whatever you're trying to average, which in this case, I'm just going to write f of x dx. So let me do the rest of this on the calculator. To start this process on the calculator, just to make things a little bit smoother, I'm going to put this f of x function in my y equals as y1. So now I don't have to rewrite it ever again. And then quitting out of there now, let me do this setup here. So I've got, let's see here, fancy fraction, alpha y equals. This is going to be 1 over 6 minus 2, multiplying that by the integral, so math 9, integral from 2 to 6 of, let me do alpha trace to pull up my y1, and I'll put an x in the dx, press enter. All of that comes out to, drum roll, negative 1.848, which gives us choice B. For this problem, we have Tara's heart rate during a workout modeled by the differentiable function h of t, and they're not going to tell us really anything else about this, just they gave it a name. We want to know which expression down here represents Tara's average heart rate from 30 to 60. Okay, so in general, average value of a function, here's the formula. Average value of f of x is going to be 1 over your interval length. We have an integral using those things you use to find the interval length. And then we have the original function inside the integrand. So applying that to this problem, we're going to have 1 over 60 minus 30. That would give us our interval length. We have an integral from 30 to 60. So already anything that doesn't have an integral in it can get tossed out here, like choice D. And then inside here, you're going to have the original function that you're trying to find the average of. So this would be h of t dt. So simplifying this, this would be 1 over 30. So that would end up giving us, let's see here, that would be choice B. On this free response problem, we're given this wacky piecewise function up here. And our first task is to find the average rate of change of f on the interval from negative 3 to 4. Well, that's just going to be f of 4 minus f of negative 3 over 4 minus negative 3. So 4 plus 3 then. So now I actually have to plug things into this function. I have a big fraction when I do this. Now the trick on this one is that we have a piecewise function, so we have to be careful about which rule we're using when we do f of these different numbers. F of 4, for example, uses this second rule here, which applies between 0 and 4. So this is going to be negative 4 plus 3 cosine 4 pi over 2, which I guess you could reduce to 2 pi if you wanted to. And then we're subtracting f of negative 3. Now negative 3 uses this first rule, so we're subtracting the square root of 9 minus negative 3 squared. And I'm just going to write 7 down here. So this is all constants. You could actually stop here and call it a day and get full credit. But if you want to keep simplifying, we could. So cosine of 2 pi, that's going to be 1. So this is just 3 times 1, or 3. Negative 4 plus 3 is negative 1. So when the dust settles, that's what that first term is. Over here, this is going to be 9 minus 9. Square rooting 0 just gives us 0. So this is minus 0. So when all is said and done, this comes out to negative 1 over 7. On this part of the problem, they want the equation for the line tangent to the graph of f at x equals 3. All right, so for a tangent line, I'm going to need an x value, a y value, and a slope, because I'm going to use my point slope formula. I already have the x value, it's 3. I need the y value to go with that. I can get the y value by just plugging 3 into the function. So we need f of 3. 3 falls in this second rule here with the cosine. So this is going to be negative 3 plus 3 cosine of 3 pi over 2, which if I want to simplify that, cosine of 3 pi over 2, that's going to be 0 because that's the x value at 270 degrees. So that zeroes out that whole second term, leaving us with just negative 3, which is a little bit nicer to write. Now we also have to figure out the slope, which is going to be f prime of 3. Fortunately, 3 is not a border value, so I can just take the derivative of this second rule here without worrying about differentiability or things like that. So f prime of x, that's going to be negative 1. So this is just for 0 to 4 now. So we have negative 1. And then, let's see here, this would be minus 3 sine of pi x over 2 times a tail of pi over 2. And if I plug in positive 3 to that, I'm going to have negative 1 minus 3 pi over 2 sine of 3 pi over 2. Yep, that's right. So what does all this come out to? Because we could simplify this a little bit. Sine of 3 pi over 2 is going to be negative 1. That's the y value at 270 degrees. Negative 1 times negative 3 pi over 2 gives us a positive 3 pi over 2. And we didn't really have to simplify anything that we've done up here. It just makes it a little bit easier to write later on. So now putting it all together in point-slope form, I have y minus my y value of negative 3, so that would be y plus 3, equals my slope of negative 1 plus 3 pi over 2, which I'm going to put in a parentheses just so I don't lose anything there. And I'm multiplying that by x minus the x value they gave us, so that would be x minus 3. And no need to simplify, so I am just done. On this problem, we're trying to find the average value of this piecewise function over the interval negative 3 to 4. So this is going to be a little bit of a mess, but let's start it off here. So for average value, we need 1 over the interval length. So that's 1 over 4 minus negative 3, or 1 over 4 plus 3, times the integral from negative 3 to 4 of f of x. Or at least that's how we would normally do it. The problem with doing that, though, is that this is a piecewise function, so we're going to need to integrate different rules about halfway through. So really what I've got going on here, and I'll put this in a parentheses here, I have an integral from negative 3 to 0 of radical 9 minus x squared dx. So that's one piece of my whole integral. Plus, I have another integral from 0 to 4 of this negative x plus 3 cosine of pi x over 2 dx function. All right, at this point we're wondering why the question writers hate us, but we're going to keep going here. So this is 1 over 7. And this first integral, this is a tough one to do with antiderivatives. It's much easier if you realize that this is really a semicircle. And in fact, this is a semicircle above the x-axis from negative 3 to positive 3. So it's got a radius of 3, but we're only taking the integral from negative 3 to 0. So really, when you get down to it, this is a quarter circle with a radius of 3. So this is going to be 1/4 pi times 3 squared for that area, and we'll simplify that in a minute. Now over here, we're actually going to need to take an antiderivative. So this is going to be negative 1/2 x squared using the reverse power rule there. Plus, so let's see here, antiderivative of cosine is sine. So we would start with 3 sine of pi x over 2, but then we have to divide by the inner tail here, which would be multiplying by 2 over pi. So 3 times 2 over pi, this would actually give us 6 over pi sine of pi x over 2. And we're evaluating just that piece from 0 to 4. All right, simplifying a little bit more now. We have a 1/7 still. This is going to be a 9 pi over 4. And then over here, we have all of this stuff with 4 plugged in, minus all of this stuff with 0 plugged in. These are all constants. You could actually stop here and call it a day. And if this is the real AP test, I would recommend you do that. But since I'm not actually taking the AP test right now, just for the fun of it, let's go and simplify. So right here, let's see, we've got negative 1/2 times 16, so that's going to be negative 8 to go along with my 1/7 and my 9 pi over 4. I have a negative 8. And before I write that down, let me see what else I have going on here. So we've got sine of basically 2 pi. Well, hold on a sec. Sine of 2 pi is 0, so this whole second term is getting zeroed out. Now, if we look over here, 0 times 1/2 negative with a square in there, that's all getting zeroed out. This is sine of 0 over here. This is getting zeroed out, so really the only thing that we end up hanging on to is this negative 8. So you could leave it like this. You could simplify it more. I'm just going to quit while I'm ahead. I think this is good. For this last problem part, they're asking, must there be a value of x at which f of x attains an absolute max on the closed interval, negative 3 to 4? Justify your answer. So really the only way to prove this one way or another is with the extreme value theorem, which says if you have a continuous function on a closed interval, you're guaranteed to have an absolute max and min somewhere on that interval. So we basically need to show, well, we already were told we have a closed interval, so that's already one piece of the EVT. But we need to show that this function is continuous on the closed interval from -3 to 4. So with piecewise functions, checking for continuity, let's first look at the individual rules. So this first one, square root of 9 minus x squared, well, we don't want to take square roots of negative numbers, but if you look at the x values we're allowed to plug in, -3 to 0, the biggest thing you're going to be subtracting from 9 is 9 if you plug in -3. Everything else is going to be smaller than 9, so you're always going to be taking square roots of either 0 or positive numbers. So we're good with the square root. Now down here with the second rule, -x doesn't have any discontinuities. The cosine does not have any discontinuities, so we don't have any discontinuities within this rule either. The only other place where you could have a discontinuity is at this border value of 0. We might have some kind of jump or something else going on. So to prove that we're continuous at the border value, we have to look at the left and the right limits there and also the function value. So checking out my left side limit as x approaches 0 of f of x, that's going to be plugging 0 into this first rule. Well, that's the square root of 9 minus 0 squared, or the square root of 9, which is just 3. Next, let's check out the right side limit at 0. Now we're plugging 0 into this bottom function here. So that zeroes out everything inside this fraction, so we're just doing cosine of 0, which is 1. 3 times 1 is 3. We have a 0 over here. So 3 when the dust settles on that limit. And then we also have to note the function value, f of 0. That's going to piggyback on the value of this left side limit because this is the rule up here we use if x equals exactly 0. So that's also 3. So we see here that the limit exists, the function value exists, and the limit at 0 and the function value at 0 equal each other. Therefore, f of x is continuous at 0. And if f of x is continuous at 0, which was really the only thing we were worried about, that means that f is continuous on the whole interval from -3 to 4. Therefore, by the extreme value theorem, f of x has an absolute max somewhere on the interval from -3 to 4.